Hello everyone, welcome to AP Physics 1, Unit 5, Torque and Rotational Dynamics Ultimate Guide. In this unit we talk about rotation. I feel like this is kind of where physics starts to get a little bit harder for a lot of people. It's a little bit harder to wrap your mind around this rotational motion idea. So kind of the breakdown of the units are right here. We start with rotational kinematics, which really just kind of connects kinematics to rotation, and how when you have that constant or angular acceleration, you can pretty much treat it just the same as normal kinematics. And then we're going to compare how to relate linear and rotational motion and really show how radius is that ultimate connecting piece of the puzzle. And then we move into torque, talking about forces on rotating objects, and then talk about some rotational inertia, and then we'll describe some of these Newton's laws in their rotational form and how it kind of brings together this whole unit. So feel free to jump around where you need. Timestamps will be in the description, and let's get into it. So the first variable that we have with rotation is the angle theta. And this theta is kind of like the distance. So I'm going to relate each one of these to what they would be in a normal kinematic sense. So the angle is the distance. And so if we put this on our circle here, we're imagining that this circle is one big object and it's rotating. So we can start it over here, and let's say it rotates this much, right? So we have our change in theta right here, and this will be our theta initial, and this will be our theta final. So that is what we call the change in theta, or the change in distance. Okay, and now we have this omega average here. And this is just the angular velocity. So that's what we call this guy, angular velocity. So this is just like velocity with our angle over time, which we said was like our distance. So it's just like the distance over time, but it's the angle over time. So the units of this is going to be, well, let me say what the units of this is going to be. If we have our angle, it could be in degrees, but a lot of times we're going to be working in radians when we're working with rotational motion. So this will be 1 radian. Okay? And so if our velocity is a radian for how much angles it goes around over time, which is still seconds, so radians per second. And now this alpha is our angular acceleration. And so this angular acceleration is this angular velocity over time, and velocity over time is just acceleration, so it makes sense. And so for our units, we'll have a radian per second over seconds, which is going to equal a radian per second squared. And so if we put these two quantities on this circle here, let's say when it's traveling from this point to this point, it's going to have some angular velocity over this point. And so it also could be accelerating. If it starts at rest and then starts rotating, there also could be some angular acceleration in one of these directions. And so note that how are we going to determine, since these are scalar, these are vectors, how do we determine their direction? Because we can't really write a direction along the curve, because we know that when we use tangential velocity, it was coming straight off, right, like this. And our centripetal acceleration went towards the center. But we're talking about this whole object spinning. And yes, if we looked at one point, we would still have our centripetal acceleration and our our tangential velocity. But when we're dealing with these angular quantities, the vector point is only going to be either clockwise or counterclockwise. So if we're moving counterclockwise in the direction that's shown here, counterclockwise, we denote counterclockwise as positive, and we'll denote clockwise as the negative direction. And it might seem a little counterintuitive being that way, but mainly the way I like to think about it is since when we define angles, we usually start at this point and go up for positive, like this. If we use like a unit circle or something, that's usually the positive angle, and the negative angle is down this way. So that's how I like to think of it to make the positive and negative make sense. And so one last thing to note here, if we're actually thinking about what an object that's spinning looks like let's say we have like a ball like this. It could be rotating along its axis, like around, like that. And that's what we call rotational motion, which is a lot different than if we had like some point in the middle and a ball was like orbiting this point and actually moving around. And so that's the difference between rotational and circular. And we'll go a lot more in depth into that in the next video, so make sure you stay tuned for that, and we'll relate those different quantities. Alright, so since we have these average quantities that are the same as in normal 2D kinematics, we can actually use those same constant acceleration equations. So this is only going to be valid if alpha is constant. And so note that alpha does not equal the centripetal acceleration. So this is going to be changing if you took any point on the object. But we're looking at the object as a whole. And the object as a whole could have a constant rotational acceleration, so we can use these equations just like we use these ones for 2D kinematics, like normal kinematics. Okay, so we'll talk more about how we relate these later, but let's do an example with these kinematic equations. Okay, so we see Bob rotates a wheel at 150 radians per second, then increases the speed to 500 radians per second over the course of 17 revolutions. What is the wheel's angular acceleration over this time period? Okay, so just like we did in normal kinematics, in really any physics problem, let's list our variables and see what equation is going to be our best fit. So we know that the initial angular velocity is 150 radians per second, and then we know our final velocity is 500 radians per second. And it doesn't give us a direction here, but we can see that it starts at one velocity and it increases to a higher velocity. So we can assume it's in the same direction, so we can just assume this direction is the positive direction. Since we know that since it's increasing, the acceleration must also be in that direction. Okay, and now we need to get our theta. But the problem is here, it only tells us the 17 revolutions, but we want to know how many radians is that. Well, if we think about a circle, if you were to go around the circle one time, how many radians would that be? Well, in degrees, it's 360 degrees, which equals 2 pi radians. And so we can actually just do this like a normal unit conversion and say in one revolution, there's 2 pi radians, and these revolutions will cancel out. And so this will equal 34 pi radians, and that'll be our angle. So you have to make sure you're in radians, or your other ones would have to be in revolutions, but we'll stick for the common unit to be radians. Okay, so now we have to determine what equation do we want to use. So if we look back at our equations, which one's going to be the best fit? Well, we know we're looking for the acceleration. We want to find the acceleration. But the main thing that's not given is the time. We don't have this time, so we can't start there, but we do have the angle, and we do have the initial final velocity, so this is going to be the equation we're going to go for. So we can go ahead and write out this equation. We have the final angular velocity equals the initial squared plus 2 alpha change in theta. Okay, and now we can just simply rearrange the equation to get alpha by itself. And so it would be the final squared minus the initial squared, and then divide by our quantities and get that the angular acceleration is equal to this expression here. And so now, since we have all these variables, we can go ahead and plug them in and get the final is 500 squared minus the 150 squared over 2 times the 34 pi. And if we go ahead and plug all that in, we'll get 1064.9 radians per second squared. And that'll be our final answer. So pretty much everything we just did was exactly the same thing you would do if you were given distances and velocities. We're just now applying this new concept of rotation in the same way. But it's important to note that we can only do that if the angular velocity is constant. That's the main thing that you have to be careful of, because if that's not constant, you can't use these equations. Just like you couldn't use the kinematics if the acceleration wasn't constant. So let's start with this very simple equation. This is where we're going to build all the other equations off of. And so this is saying the angle equals this s, which is the distance. So if we have a circle over here, and it travels by some angle, and this is the radius, this distance we call s. And since it's along a curve, we're going to call it the arc length. So that's the actual difference travel. So if you walked around a circle and you looked at like how far you traveled, that would be this arc length. And this r is just the radius. Okay? And so let's just rearrange this equation to say the s is equal to r times theta. Okay? So this is how we can relate it through this radius here. The angle traveled, we can find the radius, we can find the distance through the radius. Okay, so now let's see how can we find the velocity. So let's say we have the omega, so the angular velocity equals the change in theta over time. And so let's say we do 1 revolution. So 1 revolution, as we learned before, if you go around the circle 1 time, the amount of degrees or radians that it's in is just 2 pi. And then the time that we use to express to go around 1 revolution, if you remember from circular motion, is just the period. Okay, so that's the period. And so that's what we have this for this angular velocity. And so our tangential velocity equation that we use from circular motion is we need the distance over time. And so the distance is just the circumference, which is 2 pi r, over the time, which is 1 revolution, which is t. And so now we have this t in terms of the tangential velocity. So we can actually go ahead and rewrite this in terms of t over vt and get this. And so now that we have the period, we can actually go ahead and plug this in over to here. And so we would get the angular velocity equals 2 pi divided by this 2 pi r over vt. And so since we're dividing a fraction, we can multiply by the reciprocal and get 2 pi times vt over 2 pi r. And so these 2 pi's are going to cancel, and we're going to get the angular velocity equals this vt over r. And so if we rewrite this, we get the tangential velocity equals the radius times the angular velocity, which is in the same form as this arc length equals the radius times the theta. And so let me just box this in as our first equation. And so now we have a way to relate the linear velocity to the angular velocity. So now, just like this is the case, we can actually find that the tangential acceleration is equal to the radius times the angular acceleration. And so that's simply the definition of tangential acceleration. Because we haven't really used tangential acceleration before, we only use a centripetal acceleration. But how are we going to relate this centripetal acceleration that we talked about in circular motion? Well, we know that centripetal acceleration equals the velocity squared over r. That was that formula that we were given. But we just made a new, and this is going to be the tangential velocity, and we just have a new equation right here that we can use. So we can plug that in where we get r omega, all of this squared over r. And so now we can square this top part and get r squared omega squared over r. So one of these r's is going to cancel. And so we will get our centripetal acceleration equals r omega squared. And so that's our other type of acceleration. So if you remember, if we were taking a circle and it's traveling with some velocity tangential, this centripetal acceleration is the one that's pointing towards the center of the circle. And our angular is how fast it's speeding up around the circle. Okay, So that's how we can relate all of them, and they're all related through this r. This is the big relator, is the radius of the circle. Okay, so we can use this to do some examples. Alright, so our first example is we have a frisbee with a radius of 0.1 meters spins at a constant 100 radians per second. What is the linear speed at 0.05 from the center? And what is the linear speed at the edge of the frisbee? Okay, so let's go ahead and define some variables first. So we know the radius is equal to 0.1 meters. We also know the angular velocity is constant, so there's no angular acceleration. And so this is our radius of the whole frisbee, but we're also asked to find this point at 0.05. So the radius, we'll say, not is 0.05 meters. Okay, so let's find the linear velocity at the first point first. So we know that the linear velocity just equals the r times omega. So at this first point, that's halfway in the middle of the circle. So let's say we were given a circle here. If this is the radius, if you were at this point right here traveling with some velocity, and you'll be at this point traveling with some velocity, and we'll denote this one as velocity 0, this one at 1. So this radius is 0.05 times omega, which is 100. And so we would get 5 meters per second. And then this velocity tangent at the very edge is going to be the entire radius of 0.1 times the 100. And so this tangential velocity is equal to 10 meters per second. And so when you're at the edge of the circle, you're moving twice as fast when the frisbee is spinning at the same velocity, which makes sense because if this one makes one rotation, it's traveling a shorter distance than moving all the way along this outside, but they're both making this revolution in the same time because they're connected by the frisbee. So this outside one has to travel at a faster linear velocity even though it's rotating at the same speed. Okay, so let's do part B. So if a bug lands on the edge of the frisbee, what is its angular, tangential, and centripetal acceleration? Okay, so let's start with what we're given. So we know the angular velocity is 100 radians per second. And so we know it's a constant velocity, so the change in this velocity is equal to 0. And so since this angular velocity or angular acceleration is just the change in angular velocity, since this equals 0, the whole thing equals 0, and so our angular acceleration equals 0. But since the bug is changing its tangential velocity, because at one point, if we go back to this circle, if you're at the top of the circle, at one point it's traveling right here, but then once it's rotating to here, now you have a tangential velocity going in this direction. So it's changing, so there must be some centripetal acceleration. And so the centripetal acceleration is equal to r omega squared. And so we have all these values, so we can go ahead and plug in the radius, which is 0.1, the omega, which is 100 squared, and that's going to give us 1,000 meters per second squared, and that's our centripetal acceleration. And then finally the tangential acceleration, which is equals the r times alpha. We go ahead and plug this in, and we get, since this alpha equals 0, this whole thing will equal 0, and the angular the tangential acceleration will equal 0. Have you ever wondered why the door handle is on the end of the door, or why it's easier to unscrew a bolt with a wrench? No? Well, if you were wondering that, it's because of torque. So the torque can be defined as the radius times the force that you apply times this sine of theta. Okay, so torque we usually define as this tau guy here. And so if we want to find the units of torque, the radius, which is in meters, times the force, which is in newtons, and the sine of theta won't have a unit, so we'll express it as a Newton meter, is what you'll commonly see for torque. So let's see 3 examples. So we have like a beam that's able to rotate along this hinge here. And so let's say the force is applied at an angle right at the end of this R. The torque, for this case, we would have an angle of 90 degrees. The angle is from the force to the radius. So since this is 90 degrees, the sine of 90 is just 0. Nope, sine of 90 is just 1. So the torque will just be radius times force. But now in this case, we have some angle right here. So now the torque will have to include the radius times force times the sine of theta, which is going to be something less than 1, so it's going to reduce the torque. So now if we pull all the way so that it's 180 degrees, well, now our torque is the radius times force times the sine of 180, and this just equals 0, so our torque equals 0. And so what might seem intuitive already is that when you apply force at this perfect 90 degrees, you're able to cause this beam to rotate. And the more closer to 90, the easier it is to rotate, and if you pull it directly out, you're not going to get any rotation. So that's basically what this torque is doing, is showing how much force you're applying to rotate the beam, and it will relate directly to that angular acceleration. So let's talk about how we can use force diagrams for this. So let's say we had a situation where there was like a wall and there was like some beam coming off of it, and let's say we wanted to calculate like the net torque or something. We wanted to use like a free body diagram. So usually a free body diagram just has one point and we have like some forces coming off it like this. But in this case, our forces might not be at the same point. So we may have the gravitational torque, which we can approximate at that center of mass. So that's one force. And maybe let's say someone is standing on it, so they're applying another amount of torque on this board. And then maybe there's like a cable or something, and this applies a force. So we can draw out this sort of free body diagram, and now for each of these forces we have a radius. And now we have a bunch of different torques that we can sum up to get the net torque. And so for the example of a door hinge, let's say we have like a door like this, and it's able to rotate along here. If this is the hinge, if you apply a force to open the door at the very end, you get this force times this radius that's large. Let's have a capital R equals the torque. But if you apply it right near this hinge here, your force is going to be a very little radius to give the torque. So to increase your torque, it's directly proportional to the radius that you apply it at. So the closer to 90 degrees and the closer and the farther from where it's rotating from is going to give you the most torque. So that's the overall conceptual ideas of torque. So now let's apply it to an example. Okay, so we have Bob holds a tree of uniform mass at an angle of 15 degrees from the horizontal. The tree is 500 kilograms and is 5 meters long. What is the torque due to gravity? So we're only trying to find one torque here, and it's the torque that's applying the tree due to gravity. Okay, so let's first draw a little picture. So let's say we have Bob right here. You know, he's holding a tree. We'll say this is like the ground, and he's holding this tree like this. So we don't care about any other forces that are applying here, but we know that gravity is applying at every single point on this tree. Gravity is being applied, right? But it would be very difficult to find the force at every single point and to give a bunch of R's. And what we end up doing is to find this center of mass. That's pretty much what we do to the masses. And if we wanted to find the net torque just due to gravity, we could integrate along this whole tree and find the average at every point. But it turns out we can actually just approximate it as the force being applied just at the center of mass, which since it's a uniform mass tree, we can assume it right in the center of the tree. So this is the force due to gravity, and that's the force we want to look at. And so so now let's write our variables too. So we have the mass of the tree, which is 500 kilograms. We have the length of the tree, which is 5 meters. We have the angle, and I'm going to call this angle with the Earth, angle E, I guess. And that's 15 degrees above the horizontal. So we have this angle right here. And that's angle of the Earth. Okay. And so we also know gravity equals 9.8, obviously. And so we need to find the torque due to gravity. So the torque, in any case, is just the force times radius times the sine of theta. So we want to find the radius. We need the force, which we already discussed. This force due to gravity is what's going to cause the torque, so we can say Fg here. And we want sine, and I'm going to call this theta g, since it's not necessarily this angle, because it's the angle it makes with the radius. And so what is the radius? Well, it's not going to be the length of this whole tree, because the force is being applied right at the middle. So this radius here is going to be 1/2. So the radius will be just the length of the tree divided by 2. But then we need this angle, and so I'm going to just blow this little piece right here up into a larger triangle. Right? So we know that the force due to gravity is this piece right here. This is the angle of the Earth, and this is a 90-degree angle. So we need this theta g right here. So how can we get this? Well, we know the interior angles of a triangle is just equal to 180. So if we go ahead and sum up our angles, we know that it has to be the total angle of the interior angles minus each one of these will give us that. So the angle of Earth, and then minus is 90, and so we know that the angle of the Earth is 15 minus 90, and if we plug these in, we get 75 degrees. Oops. Should be 75 degrees. Okay. So now that we have that, we know what our angle theta g is. So now we can start plugging some more variables in. So we said r is 1/2 the length. Our Fg is just mass times gravity, because that's always what mg is. And we know the mass and we know the gravity, and then the sine will be that theta g, which we just found. And now we have all these variables, and we can simply just go ahead and plug these in. So the length is 5/2, the mass is 500, times 9.8, times sine of this theta g, which is 75. And so if we plug these in for our torque, we get this value right here, Newton meters. And so that's the torque just by gravity on this tree. Okay, now let's do one more example here. So we have, what is the net torque about this point C, which is the center point of this diagram. So we can think of this as one solid object that can rotate on this circle and the outer circle. And these are each forces, these 3 forces that are applied. So let's just start by labeling the forces. We can say this one is force 1, this one can be force 2, and this one will be force 3. And so we need to find the net torque. Now the biggest thing here is that we need to know what direction each of these forces are going. Because if a force is going counterclockwise and one is going clockwise, those aren't going to be helping each other. So let's try to define what the net torque will even be. So we know the net torque is just equal to the sum of the torques, right? That's simply just saying we sum them up. So in this case, let's look at torque 1. So torque 1 is going to be this one at force 1, and it's going in the counterclockwise direction because it's on this circle here and it's going this way. And we talked about in a previous video, counterclockwise direction, when we talk about rotation, is the positive direction. And really we could define either one as positive, but it's very typical to have counterclockwise as positive, so we will denote it as such. And so this one we can just leave as it is, but now we have our next torque, torque 2. But torque 2 is going clockwise, because it's going, around the circle like this. And so since it's going clockwise, we actually have to subtract this torque and make it negative. Okay? So then our torque 3, which is on the same outer circle, also going clockwise, because it's on the bottom going to the left, it'll also need to be subtracted. And so now that we have our correct directions, we can start plugging in what would be the torques. And so we know that we're going to have, let's just say radius 1, force 1, minus radius 2, force 2, minus radius 3, force 3. And so now we also need to make sure that our why don't we put the sine of theta in here? Well, each one of these forces are tangent to this circle. So if we say this is like the radius for this radius 1, this angle is just 90. And so this one is trying to throw you off. It says it's 30 degrees from the top. We don't care about the top. This top doesn't mean anything. We just care about where's this force on the circle, and there's this radius here, radius 2, and this angle is also going to be 90, and same thing for this force. And since all these are 90, sine of 90 is just 1, we can just disregard the sine of theta because it's perfectly perpendicular to the radius. Okay, so that's why we don't need that. And so now we need to determine our radiuses, which should be pretty simple. Radius 1 for this force right here is just this inner circle, which says 0.2. So we'll plug that in, and force 1 it gives us as 10 newtons, minus radius 2, which is this outer circle, which says is 0.5. So we have 0.5, force 2, which right here is 5 newtons, and then radius 3, which is also 0.5, is 8 newtons. And so if we plug this in to get our net torque, we just get a negative 4.5 newton meters. And so what does this negative mean? Well, we define negative as the clockwise direction, so we could also say the answer is 4.5 newton meters clockwise. And then we won't need that negative, because that negative is really just the direction of torque. So this rotational inertia is kind of describing how much mass is moving around a point of a rotating object. So this main equation we have here is this rotational inertia I is equal to the mass times the radius squared. And so the units of this rotational inertia will just be kilograms for the mass, the radius in meters squared, so we can just denote it as kilograms meters squared. And so what is this actually saying, right? Is that this is for any point of mass rotating with this radius r. So if we had like a point and there's like some mass m and it's rotating around, the rotational inertia of this ball or little point of mass is going to be I equals mr squared. But now let's say that we had like some ring of mass rotating. So let's say we have like a ring here, and I'll do it in black actually. So we have like a circle like this. Imagine this is a perfect circle, and it's like a ring, right? And so this ring is rotating around. So we can have this point, and each point of this mass, each point on this ring is a radius r. So we can just try to find one little point of mass right here, right? And we can call this m1, right? And so if we wanted to find the rotational inertia of just this one little point of mass, we would have m1 radius squared. But now let's choose the next point, another little point on this ring right here, and call this m2. So this is I1, but I2 would just equal m2 radius squared. And so if we wanted to find the rotational inertia of this whole ring that's rotating, we just have to sum up every little infinitely small point. And if we did that, we would get this equation right here. So we can see that the rotational inertia of a ring simply will just equal the total mass of the ring, we'll say m, times the radius squared. And so other objects are going to have different coefficients in the front here. Like if you had a solid sphere, you'll have a different rotational inertia than if it was a hollow sphere or a rod rotating. And we'll look at some other examples later of how you can actually calculate those, but a lot of times to get the value of something rotating just on its own, you would need some form of calculus. So for the scope of algebra-based physics, they'll likely give you what the object's rotational inertia is, but we can calculate it if we're given the center of mass inertia, and we'll talk about that a little bit later. But first, let's do an example just simply calculating and comparing rotational inertias. So in this case, we want to rank the rotational inertia of each rod about its axis. So this is the axis right here, this little dot. And so we can say this rod is rotating around like this way. And so we want to compare these. So the rod itself has negligible mass, so we can assume that the rod is not causing any rotational inertia, and it only has to do with these balls that have m. So the m represents some unit of mass, and so they're all related to each other. So let's just calculate these in terms of m for each one of them, and r obviously being the distance from each of these points. Okay, so let's start with the rotational inertia of rod A. So we know it's going to be the sum of the mass times the radiuses. And this radius is going to be from the axis, right? So they're going to have different radiuses for each one of these points. Okay, so if we try to find these sums, well, let's look at the first point. We have a ball right here that is 0.5 m. So we know that's the first mass is 0.5 m. But the radius of this, since it's right on the axis, is just going to be 0. So the radius here is 0 squared, and so this term will go to 0. So now let's do the next one. We have this ball right here of mass m, so it's just m. And now the radius here is just going to be r, because it's the distance from here to here is just r. And so that's squared. And then we need to add this mass ball right here, which is m. But in this case, even though it's r from this m to this ball right here is still rotating around the original axis. So this will be a length of this entire length, which is just 2 times r. And so now we can go ahead and simplify this to get IA, which equals, this whole term just goes to 0. We have mr squared plus, after squaring this inside, we get 4mr squared. And so this final answer for IA is going to be 5mr squared. Okay, so now let's do this for rod B. So IB is going to be the same thing. We can sum them up. Now there's no masses on this axis, and we know even if there was, it wouldn't matter. So we can just start on this first ball right here, which has a mass of 0.5 m. And the radius is just r. And then we square that, and then we add the second one, which is a mass of 2m times the radius of 2r, because again it's rotating around this axis, so we need this entire distance. So this will be 2r squared. And so if we go ahead and solve this out, we get 0.5 mr squared plus 2 times this 2 squared, which is 4, so it would be plus 8 mr squared. And then if we add these together, we just get 8.5 mr squared. And this is for IB. Okay, so now we can do IC here. So IC equals, we have this first m of 2m on this ball right here, and this is just a distance of r, plus the second ball, which is a 0.5 m, and that distance is 2r, and then we have to square this. And so just like the last three, we can go ahead and simplify these to get 2mr squared plus this 0.5 times this 2 squared, which is 4. 4 times 0.5 is 2. So we get 2mr squared. And our final answer for this one will be 4mr squared. And so now we get each of our inertia values in terms of m and r, and we can go ahead and compare these now. And we see that IB is the greatest, and then we have 5mr, so IA, and then IC. And so that's how we can compare rotating inertia. We just literally sum up each point that has mass and multiply by the radius from this axis. Okay? So let's now look at how we can calculate our own rotational inertia. So what this equation is basically saying is that we have, if we want to find a rotational inertia of some object, it's the sum of the rotational inertia of the object rotating around its center of mass plus the mass of the object times the distance from the center of mass. So the distance, from the center of mass. So let's look at this example. Let's say we were given the rotational inertia of a rod of length L rotating around its center of mass. So this rotational inertia is 1/12 ml squared. And you might see this might be given in some problem that you're having to deal with a rotating rod. So this I, we can call the center of mass rotational inertia because it's rotating around its center of mass. And we want to find what is the rotational inertia of a rod rotating around one end of the rod. So this whole rod is now rotating around like this from its end. So that's what we want to find. Okay, so we know that this I that we want to find equals the I center of mass plus this md squared. Okay, so what do these equal? Right, so we know I center of mass, this is the given center of mass that they gave us. So it's 1/12 ml squared. Now this big M is just the mass of the rod, so we can just plug in M, since we said it's a rod of mass M. And this distance is the distance from its center of mass that's rotating around. And so right here is the center of mass, so this is the distance we want to look at from here to here. And that's simply just going to be 1/2 the length of L. Like this. And so now we have all of these variables in terms of each other, so we can go ahead and start simplifying this rotational inertia. And so this is 1/2 squared, which is 1/4 ml squared. And so now we just need to do 1/12 plus 1/4, and this is multiplied by ml squared. So I'll just do that over here. Just a simple adding of fractions. So 1/12 plus, that'll be 3/12, so that equals 4/12, which equals 1/3. Okay, and so this final rotational inertia is just going to equal 1/3 ml squared. And so we notice that 1/3 is a lot larger than 1/12, and that makes sense because there's a lot more mass that's away from this rotating axis. So the more mass that's away from the axis, the larger this rotational inertia is going to be, where in this case, a lot of these locations, like here and here, are all very close, and there's a little bit outside. But at this point, there's a few mass that's close, but a lot of mass that's a lot farther from rotating, and so that will give it more rotational inertia. So rotational equilibrium is when the sum of the torques is equal to 0. So in this case, the rotational velocity is going to be constant, or it's going to equal 0, which is also a constant. And so we kind of saw something similar when we did force balances, where like if we had an object, let's say, connected to some wires, and it was holding some mass, if this wasn't moving, we could draw a force diagram that was balanced, and there would be no motion, and the sum of the forces would be equal, right? But in this case, we have where the torques equal 0. So let's say we had like some rotating, or let's do this actually. Let's say we have like a seesaw, and let's say the hinge is like right here. So now there's like a force due to gravity. Maybe someone is standing on this side, so they have like an extra force applied. And then maybe like there's like a wire of force tension. At each point, there's some torque. And so if this beam is not moving, or moving at a constant angular velocity, but in this case we'll say it's static, the sum of the torques are going to be equal to 0. So let's look at an example for how we can apply that. So in this example we have Bob has a mass of m and walks on a plank of length L. So this should be a length L, we'll say, as shown below. The plank has a mass of 2m, so we'll write that in, 2m, and is supported by a wire. So this is the wire right here. The wire can hold up to 1.5 mass times gravity. How far, x, so labeled as x, can Bob walk before the wire snaps in terms of the length of this beam right here? And so the wire will always be at the end of the beam. Okay? So in this case, we want to know how far can Bob walk before this wire snaps and the beam falls. So at any point before the wire snaps, this beam is not moving. So that means the sum of the torques before the wire snaps must equal 0. So let's label all of our different torques. So first off, Bob has some mass. So Bob is going to apply a force we'll call FB. Okay. The plank itself is going to have some force Fg, and we can approximate it as the center. It didn't say it, but this should say the plank is of uniform mass. If we want to assume it's right in the center, in most cases we will assume it's in the center. Okay, so those are two different forces pulling down on it. And then obviously we have this force due to tension that's going back up. Okay, so we can call this the torque due to Bob, the torque due to gravity, and the torque due to the wire. Okay, so we know that 0 must equal the sum of these torques. But to do the sum, we need to denote some direction as negative. And as we talked about in some previous videos, it's standard convention to denote negative as the clockwise direction. So rotating this way is going to be negative, rotating this way is going to be positive. And so this Fg and this F of Bob is all causing this torque to be in the negative direction because it's pulling down from this is where the beam is rotating. I'll just write that in orange, that's where the beam is rotating. And so this force due to tension is rotating it upwards. So that's going to be a positive torque. And so we'll want to denote that in our equation. So if we list out our torques, we have the torque due to gravity, which is going to be minus. We also have the torque due to Bob, which is also going to be minus. And then we have the torque due to the wire, which will be positive. And so I think it's easier to start with your signs of your torques and then just call the forces and the radiuses all positive, and you don't have to worry about the negative signs anymore once you have denoted them in the initial equations of your torques. Okay, so now we just need to figure out what we're going to plug in for each one of these. So the torque due to gravity, we know we need some force and radius. That's what torque equals, right? So we're going to keep the negative sign here since it's negative, and the force that is causing the torque due to gravity, we already defined it down here as Fg. And the radius, for now, we'll just denote this radius at the center as the radius due to gravity. So we'll just call this Rg for now. Okay, and then the torque due to Bob is obviously Fb. And now what is this radius of Bob? Well, we say that Bob is walking this way to the end of the wire. How far he walks is x. So x is the distance from the pivot point to Bob, which is the same as the radius, so we can call that x. Okay? And so then we have the torque of the wire, which the force is obviously the force due to tension in the wire. And the distance of the wire is at the very end of this beam, which is going to be L, the length of the beam. And so you might be thinking, what about sine of theta? But in this case, every single force that's applied on this beam is applied at a 90-degree angle. And we know that sine of 90 just equals 1. So we could write that in there, but 1 times anything is obviously just itself, so we don't need it in our equation for this case. But you do want to be careful if things are applied at an angle, you will need your sine of theta. Okay, so now what do each of these equal? So the negative force due to gravity, we know force due to gravity is just mass times gravity. And so this mass is the mass of the beam. So actually, if we want the force due to gravity of the beam, we can't just write mass times gravity, we need the mass of the beam, and we know the mass of the beam is 2m, or the mass of the Planck. So this will be 2m times gravity. And now the radius here is at the very center is where we're approximating this force due to gravity, so the radius is just going to be 1/2 the length of the Planck. Okay? And now this force of the beam, or force of Bob, is just a force due to gravity as well, because Bob is just causing a gravitational force, and we know the force due to gravity of Bob is mass times gravity, and Bob has a mass of m, so that'll just be mass times gravity, and then x, since that's what we already have, and the force due to tension. So we're trying to figure out what is the max distance he can walk. So we need to know how far can he walk before we reach this 1.5 mass times gravity. And since we're finding the farthest point, we want this tension to reach right up until this 1.5 mg. So the force of tension that's going to be applied at this right before the snapping point is 1.5 mass times gravity, and then we obviously still have L. And so now this becomes pretty simple. First off, we have a like term of mass times gravity in every single one of these. So we can factor this out and get 0 equals, I'm going to do this in black actually. So we have 0 equals the mass times gravity, and then we have this negative 2 times 1/2, which is just going to be 1, so we have negative L, minus x, plus this 1.5 L. Okay, and so this mass times gravity is just going to go to 0, because we know one of these terms have to be 0. But we don't care about the mass times gravity. We just care about this term right here. And we know mass times gravity is not going to equal 0. But we want to find what does equal 0, which is this. And so we have now 0 equals negative L minus x plus 1.5 L. And so now we can move x to the other side, and we get 1.5 L minus L, which this is like a 1 L, so we get x equals 0.5 L. And so now, no matter what, given that the mass of the Planck and the mass of Bob is constant, the amount of distance that Bob can walk to before it snaps is right at the very center of the Planck. Once he reaches the center, it'll break. So that is our final answer. So I think that's pretty cool. You can figure out when something's going to break just by using these torques equaling 0. So what this is saying is we have the acceleration, the angular acceleration, is equal to the sum of the torques over the rotational inertia, or the torque of the system over the rotational inertia of the system. And so I rewrote this just by multiplying the I to the other side. We have this torque equals I times A. And we can kind of think of this as a force equals the mass times the acceleration. And then, so we can actually use the second law to derive this equation. So let's do that. So we know force equals mass times acceleration. And when we say this, when we say acceleration, we're always talking about this tangential acceleration because we're moving in some linear motion. And so we know the tangential acceleration is just equal to r times alpha, or the angular acceleration. And so now we can plug that in and we get force equals the mass times the radius times this angular acceleration. And now what I'm going to do is just multiply this whole equation by r. And so we can always multiply both sides by some variable. So now we have r times f equals mr squared alpha. But now you may be noticing here, we have r times f, that just equals the torque. Mr squared just equals this rotational inertia, and then we obviously just have alpha, the angular acceleration. So now we have this equation, which we just derived from the Newton's second law. So pretty cool, we can easily derive it. And so really all these things are just related through radius. Radius is the big relator. And I had a video talking about how you can translate between each one of these different accelerations and velocities using radius. So yeah, this radius is very important when we want to kind of convert from linear to rotational. Alright, so let's do an example to see how we can apply this equation. Okay, so we have a 10-meter rod is released from rest and rotates about frictionless pivot as shown below. What is the angular acceleration right after the rod is released? Okay, so first of all, we need to figure out what's even going to cause this angular acceleration. Well, we obviously have some torque here because this rod is held up by nothing right now. So at this center of mass, there is some force due to gravity, right? And so this rod is going to, when it's released, is going to swing around like this. Okay? And so in a previous video, we actually derived what this rotational inertia is. And so you would either be given this or be given the center of mass rotation, then have to derive this. But for this question, I'll just give the rotational inertia, which equals 1/3 ml squared. And so that's the rotational inertia of a rod rotating about its end, because it's rotating around the end of the rod, not through the middle. So yeah, you would have to be given this or given something so that you could derive it. And if you want to see how we derive this, in a previous video where we talked about rotational inertia, we used the parallel axis theorem and derived it. It was pretty cool. So go back and watch that later if you want to see how we derive this, but for now it's just given. And so we need to figure out how we can find the angular acceleration. So we know that the angular acceleration equals the inertia over torque. So I'll just go ahead and write it in the kind of form that we are most familiar with, as the torque equals I times the angular acceleration. And so let's see, we know the length of the rod equals 10 meters, right? And that's really all we're given here. We obviously know I, and so we need to figure out how are we going to find this. So we know the torque is going to be the force due to gravity is what's causing the torque. So this is a gravitational torque because there's nothing else, no other forces are applied to this rod when it's released, times the radius. And so what is the radius going to be? Well, it's obviously applied right in the middle because we're assuming this is like uniform beam or rod. So the radius is just going to be 1/2 the length. And another thing you might be thinking here, this is going to rotate in this counterclockwise direction, or no, this clockwise direction, which by convention we're going to call the negative direction. So this should actually be a negative torque, and so we'll have a negative force due to gravity 1/2 L. Okay? And then the rotational inertia we were given as 1/3 mass of the rod, length of the rod squared, and then this angular acceleration, which is what we want to find. And so we have this mass, we don't really know what to do with it, we weren't given the mass. Well, we know force due to gravity is on this other side, and force due to gravity just equals the mass of the beam times gravity, and we still have this 1/2 L equals 1/3 mass L squared alpha. And so now these masses cancel, and also one of these lengths will cancel. And so now if we simplify this a little bit, we can say that negative 1/2 of gravity equals 1/3 L alpha. Okay? And so now if we divide over this piece, we can get, I'll write it over here so I have some space, alpha equals negative 3g over 2L. And now we know what the length is, that's the only thing it really gave us, and we know gravity obviously. So we can now plug in these values here, which is, okay, and then 2 times length, which is 10. And so we get a negative 1.47 radians per second squared. And so what does this negative mean? Well, simply just the direction of rotation. So the acceleration is also in this negative direction. So we could also write this as the angular acceleration is equal to 1.47 radians per second squared clockwise. And that has the direction. Since these are vectors, we do need the direction, and so that will be our final answer. Okay? And so now you might be thinking, does it matter when we're calculating this? Is this angular acceleration constant? And the answer is no, it's not constant. And let's see why. So let's consider the rod has rotated and now it's at this bottom position as shown here. So it started up here, this was the rod, and it swung down and now it's in this position. Well, now we know the rotational inertia is still going to be 1/3 mr squared, nothing changed there. The length is still 10 meters. But now we need to find what torque we're going to be using. We still have this Fg like this, right? And so if we write out our equation, we still have the torque equals the I times the alpha times angular acceleration. So I did actually mention last time, but we used the force due to gravity times R equals I times alpha. But I didn't mention the torque, of course, needs to be multiplied by sine of theta. But in this first case, we had an angle of 90 degrees right here. So sine of theta is just going to equal 1. So we don't even need it if it's perpendicular. But in this case, our theta that this angle is making to the rotation is 180 degrees. And so if we take sine of 180, force times gravity, R equals I times angular acceleration, this just goes to 0, so everything is going to go to 0. So if this equals 0, this whole side equals 0, and we know the rotational inertia doesn't equal 0 because it equals this. The radius is going to be positive, the mass is going to be positive, so this does not equal 0. So that means this alpha, this angular acceleration, must equal 0. And so that's why it's changing. So as this rod rotates down, it's losing acceleration as it gets down to here. And once it hits here, the angular acceleration equals 0. And now let's say the rod is up here. Now this angular acceleration is going to be in the opposite direction because the rod's going to start slowing down. And this angular acceleration is actually going to be positive since we defined it as negative originally. It's a negative value. It's now going to be positive because it's going in the counterclockwise direction. So it's important to note that the angular acceleration in this case isn't going to be constant because the torque is changing this angle. And which makes sense because if it was constant, it would just start swinging around this pivot at a constant rate. But we know that doesn't happen, obviously, if you were to drop it, because gravity is now going to be affecting it in the opposite direction in terms of rotation, even though the force due to gravity is obviously not changing its direction. Just where it is relative to the pivot changes, and that's why your angular acceleration is going to change. And so that's why it's 0 in this case. Alright, so that's all of Unit 5. Thanks for watching this video. Feel free to go back to any sections you need. We'll be jumping into Unit 6 next, where we start describing how to relate momentum and energy to these rotating objects and how those can be in the same problem together. So it gets a little tricky. So make sure you stick around for that. And thanks for watching this video.